Another very important characteristic of a star is its mass, and it's not very easy to get. It's not as easy to get as the temperature, where you can measure the spectra and determine it. So how do we get it? Well, binary systems turn out to be very important in being able to obtain information about mass. And many of the stars out there are binaries. They orbit their common center of mass, as shown here. It's kind of like a seesaw or a teeter-totter. If you put a large kid on one side and a light kid on the other side, for giving them the balance, the bigger kid has to be closer to the pivot point. If you throw a hammer up into the air, it orbits its center of mass, which would be close to the head, closer to the larger mass side of the hammer. Well, it's traditionally been understood that over half of the stars in our galaxy are binaries, although I put a question mark there because recent research is challenging that, but nevertheless, many stars are binaries, so they lend themselves to study. It's not a rare occurrence. Well, you can apply Newton's version of Kepler's third law to get specific information about this. Kepler's third law relates the period and the orbital radius of planets in particular as we investigated it. So the period squared is equal to the orbital radius cubed, years in astronomical units. So that's Kepler's third law. Well, this is valid in our solar system with a one solar mass object in the center. So this is all based on the fact that we have our sun, which is one solar mass. And so the mass of the sun is equal to that ratio. So that ratio is equal to the mass of the sun. And that's actually Newton's version of Kepler's third we encountered. One solar mass is 1 cubed over 1 squared, etc. It works for all the planets. Wonderful. The Earth, all the planets besides the Earth, all the asteroid belt, the Kuiper belt, the Oort cloud, all the mass of the solar system is almost all contained in the sun. So just to give you a perspective on that, it's incredible. If this represents the sun, this whole orange circle, then this little sliver here represents all the mass that's not the sun. It's only 15/100ths of 1%. So the sun is 99.85% of the mass of the solar system. Hard to imagine. That includes Jupiter as well, which is 318 times more massive than the Earth, etc. So the sun has got it almost all the mass. So the sun doesn't hardly move at all compared to all the planets orbiting around it. If you look at the motion of the sun, it's very slight. So you can assume that it doesn't move at all, and that's one reason why that formula works. It turns out for binaries, you have a significant amount of mass that's orbiting the other. So mass A and mass B. And it turns out that if you add those masses, the addition of the two masses equals this ratio. We can get the ratio, then you know the sum of the masses of the system. And that's very useful for astronomers trying to obtain information about the mass. In some cases, they can actually get the masses, because if you know the total mass of the system, if you know the total mass, and you get that the sum of the mass is this, then you can get the mass of each particular one. So that's very useful, very powerful tool. So binaries give us information about the mass. What kind of binary systems can we have? Well, there are 3 different classes of binary systems. And perhaps the most intuitive one would be visual binaries, where you can actually see them. You can point a telescope and separate the two stars optically and actually be able to see both of them individually. So here's a case in point. We have Sirius A and B. Turns out that Sirius B is a real little star quote unquote. It's a white dwarf, so it's really an ember, but nevertheless, same principle. It's shining bright enough to see it. And here's different positions of those two stars over decades of time. And from 1900 to 1970, you don't see this very often, but we've had the privilege of observing these stars to the extent that the orbital characteristics have been able to be specified. The angles of the orbits, the periods, and the relative masses, all that has been determined. It's got a period of about 50 years. The masses have been determined, so that gives us a foundation to understand the stars in much greater detail. In addition to visual, we have eclipsing binary systems. Very important, probably the most important category, would be fair to say. So the problem with binaries is usually we don't know the inclination of the orbits. I mean, you look over here and at what angle is the plane of the orbits of the two stars? Is it face on, edge on, somewhere in the middle? Usually it's somewhere in the middle. So because of that uncertainty, it leads to uncertain masses as well. However, if one star eclipses the other, we know for sure that their orientation is edge on, so that's very useful. So just as an example, we have a lot of possibilities here. When we have a system like this, where one star is partially eclipsing the other, we get these triangular patterns. When both are in view, the light is the combination of both, so it's bright. Then when it goes behind, it might have a different dip in the light intensity. But by studying this, you can gather information about whether it's a partial or total eclipse and the relative brightness of the stars. Here we have a total eclipse, a small bright one orbiting a large dimmer one, and that produces a different characteristic pattern. The light curves. When the bright one is in front of the dim one that's large, the dip isn't as deep. And you can measure the time it takes to transit and all that and get a lot of information. So the particular light curve reveals a lot about the nature of the stars that are involved in the binary. Eclipses can be many different combinations: partial, total, big, small, hot, cool, and in fact they are. Turns out this is the method that's used to find extrasolar planets significantly in recent times. The Kepler mission is using the eclipsing method of a planet transiting across its parent star to determine characteristics about that planet. So the third type of binary is spectroscopic binaries. Recall, of course, that the stars are very far away, so most binary systems cannot be revealed through telescopes that can separate the stars visually. And we usually don't have the wonderfully fortuitous situation where the stars are seen edge on, so we see the eclipse. Nevertheless, we can look at their spectra. And sometimes their spectra will reveal an interesting feature, namely that the absorption lines are blue shifted part of the time and red shifted part of the time. Well, that just corresponds to the fact that one star is orbiting the other, and as a star moves toward, it's blue, and away, it's red shifted. So that's why it's called spectroscopic. So in this way, the spectra will reveal the nature, specifically the speed. You can get the speed of the orbit, and by observing this for a while, you can get the period. A wonderful example of this is Mizar, which is a star second from the end of the handle in the Big Dipper. It's very easily seen with the unaided eye. And there happens to be another star with that, Alcor. And Alcor, if you look at it, you think, oh, look at that. There's a binary system. Turns out that's an optical double. It's not really a binary. Optically, you can see that star, Alcor, right next to it, but it's not gravitationally bound to Mizar, so it's not part of the binary system. But Mizar itself, through a relatively inexpensive telescope, can be separated visually. It's a visual binary, Mizar A and B. But that's not all there is to the story, because both Mizar A and Mizar B are both binary systems in their own right. However, that is only revealed spectroscopically, as we just discussed. They're too close to separate visually. So here they are, graphic form. So we look at one of the stars of Mizar, and as we study that, we see how it's blue shifted and red shifted around the unshifted spectra absorption line here. You can see the small amount of shifting of its spectral line. in so doing revealing that it's a binary system. So those are the three types of binary systems that we investigate. So the mass that we just investigated, the most fundamental property of the star, it turns out. Here is shown to scale some main sequence stars. The mass actually can determine their luminosity, their temperature on the surface, the radius, the lifetime of the star. And there's huge differences that are highly dependent on the mass. Turns out that hot, bright stars, okay, with large mass, they burn so furiously, they burn so quickly, that they die out sooner than a smaller star does, even though they have more fuel to burn. They disproportionately burn their fuel quickly. Because of that, it turns out that if you find a massive bright star somewhere in the galaxy, it indicates that stars are being born because they are very young stars. Because there is no such thing as an old massive star. Because if they're massive, they go through their life cycle very quickly. There is a relationship between mass and luminosity. It probably is intuitively obvious that as the mass goes up, mass compared to the mass of the sun, the luminosity compared to the luminosity of the sun likewise goes up. This data here shows the particular way in which that happens. So there's this is a logarithmic scale. Notice it's not linear. This is a factor of 100 with each increment here, and on this side it's a factor of 10. So if you quantify this, it turns out that the relationship is as follows, that the luminosity of the star is related to the mass, particularly to the 3.5 power of the mass. So mass to the 3.5 power. It's kind of strange. So as mass goes up, the luminosity goes up very quickly. You double the mass, the luminosity goes up way more than doubling. It goes up by maybe a factor of 12 or whatever 2 to the 3.5 is. The lifetime of the star, likewise. Well, because with greater mass, the luminosity goes up so rapidly, it turns out that with the greater mass, the lifetime decreases pretty quickly as well. Bigger star, but really ferocious burning. So the lifetime is related to the inverse 2.5 power of the mass. So there's some quantitative information that relates luminosity, lifetime, and the mass of the star. So let's look to see how the mass is related to the main sequence on the HR diagram and how it affects the lifetime of the star. We know again that if it's on the main sequence, the star is fusing hydrogen into helium in the cores. So that's 90% of the stars doing that. Or you could say that a given star is on the main sequence for 90% of its lifetime. So most stars are on the main sequence. Well, the position along the main sequence turns out to be highly related to its mass. Of course, we know the HR diagram shows temperature and luminosity. But what determines what those luminosity and temperatures are? Well, it's the mass. The mass turns out to set the rate at which the fusion takes place in the core, so it sets the balance point between gravity pulling in and internal pressure shoving out to produce the hydrostatic equilibrium that every star must maintain if it's going to be a stable star. And main sequence stars are stable stars. So mass is the most important feature of that. Fusion is very sensitive to the mass. Let's take a look at a 10 solar mass star. 10 solar masses right here about. Turns out it's not just 10 times as bright as the sun. Here's the sun. Luminosity 1 solar unit. If it's 10 times the mass of the sun, it's about 10,000 times brighter than the sun, not just 10 times brighter. So a luminous star in the main sequence, if it's luminous, it's hot or large or both. Right? The mass is bigger too, but it doesn't increase as fast as the luminosity does, as we just saw. Because as you increase mass, the luminosity increases faster, the larger star must burn out faster. That's just a necessary logical consequence. As a for instance, this 10 solar mass star, 10 times the hydrogen fuel. So if you think, okay, I've got 10 times the fuel, it should burn 10 times as long if it's burning at the same rate. But it's burning 10,000 times more rapidly. Therefore, it only lasts 1,000th the time that a 1 solar mass star would. So it burns out 1,000 times quicker. At the other end of the spectrum, if you have a star that's only, say, 0.3 times the mass of the sun, it has a luminosity that's only 1/100th the luminosity of the sun. So it's burning its fuel much, much slower than the reduction in mass would indicate. And so it shines actually 0.3 over 0.01, or 30 times as long as the sun. A lot longer than you might expect, just being about 3 times smaller. So that would burn for literally 300 billion years. So these smaller stars, actually, anyone that's been born has never burned out, because the universe isn't old enough for the star to have used up all of its hydrogen fuel. So hopefully this gives you a clear perspective on how dominant the mass of a star is and how it affects the lifetime of the star. And certainly that's all related to how prodigiously it produces its energy, or how bright it is. Sort of as a review to all the characteristics we associate with an HR diagram, there's quite a few, and fundamentally it's a diagram showing luminosity versus temperature or color or a spectral class. All those things are on there. And it shows the distinct positioning of the various luminosity classes. We have the main sequence, giants, supergiants, and white dwarfs. Lines of constant stellar radii are related to temperature and luminosity, but fundamentally those are related to the mass of the star. The masses and the lifetimes are listed along the main sequence. We see increasing mass here. Correspondingly, there's a decrease in the lifetimes of the stars. Examples of stars of various spectral classes and luminosity classes are listed throughout this diagram. So that gives you some good examples of stars associated with those. And this will conclude our basic overview of the characteristics of stars.